So today we'll continue our discussion about synchronization and concurrency in Android, and what we're going to be focusing on now is some of the mechanisms that Android provides for synchronization and scheduling of concurrent applications. So the particular mechanisms we're going to talk about are largely based on what's available as part of Java, and then next class, we'll talk about some of the Android-specific kinds of things. To motivate this particular application, imagine you're producing some kind of producer-consumer software that runs in multiple threads and implements some sort of synchronized buffer or synchronized queue or bounded buffer. These go by various names. And you'd like to be able to make sure that as you put things into the buffer, if the buffer is full, you want to wait, and if the buffer is empty, you want to wait, but otherwise you want to make sure that you can correctly and efficiently pass the information between multiple threads, at least two threads, using this synchronized buffer or synchronized queue. Now, there's a couple of issues you have to think about if you're trying to do this. One of which is if you don't have any kind of locking whatsoever, then as the different threads try to put and take from this bounded buffer, they're going to end up corrupting the internal state. And we'll come back and look a little bit more about that in a second. The second thing you have to be careful of when you build something like this is if you end up in a situation where you just busy wait, you just spin, and when there's nothing in the buffer, you just spin and waste a lot of CPU cycles. So those are the two undesirable circumstances we'd like to try to avoid by the design we're about to talk about. So here's a little bit of sample code that will help to illustrate the problem that we're dealing with. So we have a class called synchronized queue, and we have a bunch of methods and data in there. Let's kind of walk through it step by step. So we're actually going to implement this synchronized queue using some kind of resizable array list, which is a type of list that can grow or shrink. You can add things to it, you can take things out of it, you can resize it. We're also going to define a couple of methods, put and take, which are used to enqueue and dequeue strings into the queue. It's obviously not difficult at all to generalize this to work on any type. We're just using string to make this easy. Later on, when we talk in more detail about some of the more advanced patterns for this, I'll show you how it works in Java. And finally, we define a couple of threads that are spawned inside the main function. And these threads are going to do two things. They're going to spawn runnables, and one thread is going to go ahead and generate a bunch of messages, and the other thread is going to consume those messages and print them out to the standard output. So here's a couple of questions for you. What is the output of this program going to be the way that we've written it here, the way that it's currently implemented?
Is the main thread joining on the first one, or is it just going to?
Let's assume it does something or other, but it's actually sort of a trick question, but the question is, what do we know what the output is going to be? And why not?
We don't know how the scheduler is going to work.
So we don't know how the scheduler is going to work, but even more importantly, we don't know whether the queue itself is going to be corrupted, because we have one thread that's writing to this thing and one thread that's reading to this thing, and you could end up corrupting data structures, and all kinds of strange things could happen, especially on a multi-core platform where these threads are likely to actually execute simultaneously in parallel. So what we need to do a bunch of things. First thing we need to do is we need to make sure that we are only allowing one of these methods, either put or take, to execute inside the context of this object at the same time. And there's a real easy way to do that in Java. We apply the synchronized keyword. So as we'll see later, the synchronized keyword says that only one method at a time can be active in an object, even if multiple threads are calling methods on that object simultaneously or concurrently. So synchronized has this concept of locking or mutual exclusion. And as you can see, it's really easy in Java to add the synchronized keyword. We'll talk a lot more later about all the nuances in this particular construct, but that's a good starting point. Okay, there's still a problem with this solution, though. Does anybody see what the problem is still going to be here? So we don't have to worry quite so much about the data structure being corrupted, but we still have to worry about some other things.
Multiple threads will not be able to meet if you have more threads, because reading does not need to be protected.
Well, let's see. So in this particular case, we're not reading, we're taking. So we don't, if we were going to peek, for example, we're dequeuing in this case. If we had a peek method or something that would read it, then you're right, we'd want to do something different.
If the queue is empty and you take, you're not going to block, you're just going to crash.
Or spin.
Here you might crash.
Here we might crash. Yeah, bad things will still happen. The data structure internals might be preserved, but other things are going to go wrong. So the question is, what do we do about this? How do we fix this particular problem? Well, there's a variety of ways to do this. We're going to talk about one of the simplest ways of doing it in Java using something called monitor objects. By default, all Java objects have the potential to be monitor objects. We'll talk a bit more about that as we get a little bit further along. And what that means, we'll also talk about a little bit later on, but it means that all objects have the ability to be synchronized. Methods that you want to have synchronized need to be marked in one of several ways. One way to do it is to actually put the synchronized keyword in the signature of the method itself. So for example, here's an example where we have the put method be synchronized and the take method be synchronized. We'll look at some other variants of this later on. And if you do that, then what will happen is that only one thread at a time will be allowed in there. There's a nice description about this at the Java website. So synchronized methods basically take turns. It's kind of like using a restroom in an airplane where you have this mutual exclusion. If you want to get to the restroom and it's vacant, then you can come in and you close the door and it becomes occupied. And when you're done, you leave and it becomes vacant again. So it's kind of a one person at a time kind of model. There's also something else Java supports. It also supports, in addition to synchronized methods, it also supports synchronized blocks, which are more fine-grained. So with synchronized methods, the entire method is synchronized. Access to the entire method is synchronized. With a synchronized block, only access to that block of code in the method will be synchronized. So here's a simple example where we're removing the synchronized keyword from the method signature, and we're making it be part of the implementation of the method. So now just the part where we're going to be adding something into the queue, the underlying array list is going to be synchronized. An interesting question is, what are the pros and cons of having synchronized methods versus synchronized blocks? And the main issue is that you end up with the ability to have finer level granularity of locking. You don't have to lock the entire method. You can only lock a part of it where mutual exclusion is necessary. And there's more discussion about this at this website as well. Now, before we move off this topic, it's worth just taking a step back and asking a few thought questions. So what would be the reason for using synchronized blocks? What would be a reason for using synchronized methods over synchronized blocks? I told you that synchronized blocks have the ability to do finer level concurrency control because you're only locking the specific parts of the code that access data that's actually shared by multiple threads. But there might still be a motivation for having synchronized methods instead.
Synchronized methods document your threading policy, so when somebody extends your class, they automatically know that synchronize means synchronize on this rather than synchronize on some inside lock.
So synchronized method is a bit more self-documenting. It gives people a better sense, perhaps, of what's going on. That's one answer. Of course, you could argue that it should be documented via some other means, but that's a good point. Can anybody think of any other reasons why you might prefer to use synchronized methods versus synchronized blocks? So if you're running on a computer that only has one CPU, and you put lots and lots of synchronized blocks in your code, there's largely ever only going to be sort of one thing that's going on at a time. And by having all this fine level of locking granularity, locks will be acquired and released quite a bit, even though there really isn't much opportunity for parallelization to be improved. So you're better off thinking about more fine-grained locking strategies to the extent that you've got more processor cores or more processors at your disposal to actually get a win from greater concurrency, or parallelization in this case. Otherwise, you're just going to slow things down for no particular win. Although if you're trying to future-proof your code, then you may be developing for a single CPU now, but anticipating moving to a multi-CPU environment where that might be more beneficial. In addition to synchronized methods and synchronized blocks, which by the way, are very simple-minded ways of being able to handle synchronization. They do a good job with serialization, but synchronization often means more than just making sure only one thing is happening at a time. Java objects also provide several other mechanisms as well. And they have these methods called wait, notify, and notify all. And these can be used to allow callers to wait for certain conditions to become true and or inform other waiter threads that the conditions have become true or may potentially have become true, thereby giving them a chance to take up again and continue to execute. So as you can see in this little code fragment, and later we'll look at some more detailed examples of how this works, but for now, whenever you want to take something from a queue and the queue is empty, then we go ahead and we wait. So we wait for the queue to be not empty. Likewise, when someone goes ahead and tries to add something to the queue or put something in the queue, after we add it, we may not want to notify waiters that there's something in the queue, and they may be able to wake up and make progress. So basically, when you call wait on a thread inside of a synchronized block, like we're doing here, that will cause several things to happen, the most important of which, for the moment, we'll talk about more of this in a second, but for the moment, it's going to end up putting the thread to sleep until it gets notified by some other thread. Calling notify all wakes up all the threads. And we'll talk later about notify versus notify all. There's a nice article that appears in Stack Overflow that talks about why you would choose to use notify versus notify all. If you design your software properly, you can often get by with notify, which just wakes up one thread. If you don't design your software properly, you may have to use notify all, which will cause lots of threads potentially to wake up. And we'll talk later about what it means to design your concurrent software properly. As a general rule of thumb, for very, very simple types of interactions, you can use the built-in Java synchronized methods and blocks and the condition that comes with every object that wait, notify, and notify all use. For more sophisticated kinds of interactions, such as things like a synchronized message queue, you may actually want to use a slightly different approach. And we're going to look shortly at another way to do this that is based on how the implementations work inside of the Java concurrency libraries themselves. So let's take a little bit more detailed look at what wait and notify all are doing. So inside of a synchronized method or a synchronized block, you can have a thread request to wait on some condition. Now, by default, every Java object that has synchronized methods or blocks has the ability of having a waitable condition, one waitable condition, which is implicit. It's called implicit conditions. We'll talk about that. And so, for example, when we come along and call take, which is a synchronized method, it's going to implicitly acquire the monitor lock, which you don't ever see here directly. That's just implicit in the way that Java concurrency works. So when you have a synchronized method or a synchronized block, that automatically acquires the one monitor lock for the object. It then checks to see whether the queue is empty or not, checks the queue size. And if it is empty, it goes ahead and waits for the condition to wait. It waits. And what it's waiting for is for the condition, which is implicit, to be notified by a call to notify or notify all. A couple important things to note here, and we'll talk about this later. When wait is called, when you call wait, that automatically releases the monitor lock and puts your thread to sleep. Those two things happen at the same time. Some important things to remember. What I'm about to say is never violate this unless you absolutely know what you're doing, and even then think twice about it. So it's almost always the case that when you do wait calls, you want to put them inside of a loop, typically a while loop. So you typically say something like, while some condition is true, wait. And later on when we see what notify and notify all do, it may turn out that when you're notified, the condition actually isn't true. So you may have to go ahead and wait again. Or sorry, the condition remains true, and so you have to go back and wait again. So just because you've been notified doesn't mean that the condition you're waiting for has necessarily been satisfied. So you can't typically rely on the fact that you've awakened from wait to know with any kind of assurance that you've got the resource that you want. And we'll talk about that a little bit later. There's some nice discussions about this on the Java concurrency page that talks about guarded methods. These are basically guards. These conditions are guards. So a thread will keep blocking on a wait call unless two things happen. One of two things happen. One, you can use a timed wait call where you give it a timeout and it'll block up to that amount of time. Or you wait until some other thread notifies the waiter that there's something to do. In this particular case, that there's data to process. The queue is no longer empty. So in that case, you'd wake up. And the way that that works is that the thread that does something that changes the state of the queue, like it goes ahead and puts some data in the queue, is responsible for calling notify or notify all. In this particular case, we have to use notify all. We'll look later at a more optimized case where you don't have to use notify all. So once notify all is called, that will cause all or at least one thread to wake up, and it should cause all the threads to wake up. One of them will get a chance to run, and then it will then be able to check to see if the queue is empty, and then it'll do its thing to remove the data. After the thread is notified, it wakes up, reconsiders its condition. If the condition is no longer true, then it falls out of the loop, does its thing, which in this case would be to remove the element from the queue. And then as you exit the method that was synchronized, or the block that was synchronized, the lock is implicitly released. So you are not responsible for doing anything to acquire and release the lock yourself using this particular way of doing things. And as you'll see later, the Java built-in concurrency and synchronization mechanisms are very simple. They work for simple use cases. They're real easy for simple things. They get a little tricky when you start trying to do something that's more ambitious, and I'll talk about that shortly. OK, so to go ahead and summarize this discussion, each Java object can be used as a monitor object. If you need to have mutual exclusion, then you have to mark them with the synchronized keyword, or you have to use the synchronized block. Either of those things work to get the desired effect. What you typically find, by the way, and it's actually kind of instructive, take a look at the Android source code for some examples of this. Simple solutions typically use synchronized methods. More sophisticated solutions, solutions that are meant to use more sophisticated locking mechanisms or condition mechanisms, or which are expected to run in more highly concurrent parallel environments with multi-core chips and so on, they tend not to use synchronized methods. They may use synchronized blocks. In some cases, they'll actually use other kinds of locking mechanisms directly. And I'll show you some examples of that when we get a little bit further on to the next section. Each monitor object, by default, is equipped with a single wait queue in addition to its single entrance queue. So the entrance queue is really used to make sure that only one method at a time gets access to the method. That's what's called the monitor lock. And then there's also this wait queue, which corresponds to the implicit condition. So if you're interested in learning a bit more about this concept, take a look at the Wikipedia article on monitors and read about implicit condition variable monitors. Java objects, by default, are implicit condition variable monitors, with all the pros and cons that come from that. Production Java apps, like many of the things you'll find in Android, actually need more than what you get out of the box in Java. Out of the box with Java monitor objects. This other stuff is part of Java 2. These are part of the Java util concurrent package, and this is the locks package in that other package. And if you take a look at the website, you'll find that they have a number of interfaces and classes defined that do all kinds of useful things. So they have things called locks, which are basically mutexes. They have readers writer locks, which go back to what Shweta was talking about with respect to being able to allow multiple readers to simultaneously access something as long as it's not changing. But if a writer comes along, only one writer at a time is allowed to make any changes. And then they also have something called conditions. And conditions are used to basically allow yourself to be put to sleep until the world changes in a way that satisfies what your needs are, what your conditions are. And there's various classes that implement these kinds of things. There's also other mechanisms available in other parts of the Java util concurrent package. Things like semaphores, for example, are also part of that package. And they give you other ways of being able to do synchronization and scheduling. OK, so are there any questions about the basic mechanisms in Java for monitor objects? Cool stuff, pretty straightforward to do. Now we're going to talk a little bit more generally about the monitor object pattern. Because what you see in Java is a variant, actually to some extent a stripped down variant of a more powerful pattern that's been around in computing for many decades. We wrote this pattern up as part of a book called the Pattern-Oriented Software Architecture Volume 2 book, which talks about patterns for concurrent and distributed objects. And so monitor object appears in that book. You can also download a paper from my website that talks about it as well. So the intent of the monitor object pattern is to synchronize concurrent method execution to ensure that only one method at a time is active within an object, irrespective of how many threads are trying to access that object. So that's one thing it does. That's sort of the serialization portion. And then the second portion is it allows the object's methods to cooperatively schedule their execution. So they can take turns getting things done in a cooperative fashion using these wait and notify all types of operations. And so what we're going to do now is we're going to take a look at this as a pattern, and we're going to look at the different nuances of the pattern. We're going to talk about different ways that the pattern can be implemented. I'll show you some examples from a couple different variants of how this is done in Android, and it'll give you hopefully a real good idea of how this stuff works. You'll find that monitor objects get used quite a bit in many languages, not just Java. Okay, so when would you want to apply this pattern in the first place? So you would want to apply the monitor object pattern under several circumstances. One is when you want the methods in an interface to an object to define its synchronization boundaries. So you want the method call, when you call a method, you want that to be the boundary of synchronization. There are other ways of defining synchronization as well. The method call doesn't have to be the boundary. There are other languages that have different styles of concurrency where the method call isn't necessarily the boundary. There's other models where you might break things down in finer level granularities, sort of like the synchronized blocks we were just talking about, or you could even do things where you're just kind of free threading. You're not really trying to have methods involved at all. You're just grabbing locks in somewhat spaghetti-like fashion. Not necessarily the most desirable way to go, of course, but it's a way to do things. You also want to make sure that in this model, apply it when you only want to have one method at a time that can run within the object. And if you have more than one thread at a time, something horrible has happened, and you're going to have race conditions and scheduling hazards and data corruptions and those kinds of things. Likewise, you'd also like to be able to have the objects responsible for the method synchronization transparently and internally without requiring anything other than making the method call itself. So the user, the client of this thing, should just call a method. They shouldn't have to know about grabbing a lock, doing some work, releasing a lock. All the locking mechanisms from a client's point of view, in other words, the caller's point of view, are encapsulated and hidden. The implementation is not visible. It's encapsulated, as it were. And another reason when you might want to use this pattern is if the methods in an object may need to block during their execution. If the methods don't need to block during their execution, you can get by with a simpler model. You don't need to use the monitor object pattern. Or you could look at it as a very simple, lightweight use case of the monitor object pattern is when there's no blocking involved. Then it's basically just synchronizing access or serializing access to the state variables without worrying about waiting or notifying. So here are essentially the key structure and participants in the monitor object pattern. And we're going to talk about them. It's fairly straightforward. It maps very nicely back to the examples we looked at. And in fact, I'll kind of map this back to the example we talked about before with our synchronized queue use case that we were talking about earlier. So you've got a client, someone who's making method calls, and we typically assume that there's going to be multiple clients. It doesn't get very interesting if there's just one client in one thread. Then what's the point of having synchronization at all, for the most part? So let's assume that there's multiple clients and multiple threads making invocations. So the first thing is the monitor object itself. And the monitor object consists of one or more synchronized methods. Now, to go back to the point we made earlier, they might be synchronized by virtue of the fact that they have the keyword synchronized in their signature. But that's not necessary. It's not necessary in Java to do it that way. And certainly in other languages that don't support synchronized methods as a keyword, like C or C++, you would implement this pattern, but the methods would be logically synchronized, but they wouldn't have the synchronized keyword there. And that's actually very, very common. In our particular example, the synchronized queue played the role of the monitor object in the monitor object pattern. Then we also have a monitor lock. and it typically has methods like lock, unlock, or acquire and release. It goes by different names. In the case of Java, it's the Java monitor lock, and it's implicitly acquired and released every time a synchronized method is called and returns, or every time you enter and leave a synchronized block. That's the second thing. And then the third thing is the monitor condition. And as you see from the UML diagram here, you can have 0 or more monitor conditions. In Java objects, the simple ones, you always have 1 monitor condition per monitor object, unless you take steps to have more, and we'll see some examples of how to have more. In other languages, of course, that don't have implicit monitor conditions, you have to define them, and that's what you would do. And they would typically have operations like wait, notify, notify all. Some systems have wait, signal, broadcast. They go by various names here. The key idea is that you have a method that blocks, waiting on something to change, and then you have other methods to wake things up. So as we said before, Java monitor objects only have one implicit monitor condition. All right, any questions about the structure diagram? Pretty straightforward. One of the nice things about monitor object, as we'll see later, it looks quite a bit like normal objects. In fact, that's part of its appeal. It doesn't look a whole heck of a lot different than a regular old object that doesn't have locks. It just has this wonderful property that if multiple threads call it, they're protected from concurrent access. Now things get a little bit more complicated. And this is an interaction diagram that we have from the POSA2 book. It's a little small. If you take a look at the slides, you can kind of make it out. And it looks kind of complicated at first. It's actually quite simple, but it's showing you all the various steps in the canonical interactions for the dynamic portion of the pattern. So let's just break it down. First of all, notice that there are 2 threads, client thread 1 and client thread 2. And we have some monitor object. Let's assume, for sake of argument, this is the synchronized queue monitor object, just to make it interesting. And let's assume, for sake of argument, that the first thing that's going to happen is someone's going to try to call the take method. So when you call take, let's say thread 1 comes along and says take. It wants to remove a message from the queue. Let's assume, for sake of argument, the queue is empty. So what will happen in that case is that we'll call take, which is synchronized method 1 here. That will implicitly acquire the monitor lock, and then it'll try to do some work. Well, the first thing it's going to try to do is it's going to take a look and say, is this particular queue empty? And the answer is yes, it is empty. So what do we do in that case? Well, what we do in that case is we turn around and we say, I'd like to wait, please. And you wait on the implicit monitor condition. And remember, when you wait, the 2 things happen atomically. The monitor lock is released, and the thread that calls wait goes to sleep. Very important that those things happen atomically. Otherwise, you can end up with things like lost wake-up bugs and other kinds of problems. So at that point, thread 1 is fast asleep. Now, thread 2 comes along at some point later, and it calls put. So it's actually going to enqueue something. It's going to try to enqueue something into the monitor object, into the synchronized queue. Well, what that does, of course, is it acquires the lock, and it does some work. In this case, what it does is it turns around and it puts the message into the array list. So now there's actually something there. And then it turns around and it calls notify. It actually calls notify all, but it notifies somebody. It doesn't really know who. And on its way out, it also goes ahead and implicitly releases the lock. So when we're all done here, the lock will be released. And now this first thread, which was asleep on a wait, will wake up, reacquire the lock, loop around and say, is this queue empty or not? And let's assume, for sake of argument, that it's not empty, because someone just put something in there. It will then go ahead, remove that element, return it back to the caller, and release the lock on the way out. So those are the other steps that are going on here. Couple questions, yeah?
When the first thread stops the first time, does it release that lock?
Yes. When the thread first stops, when we have synchronized method thread suspension, that will do 2 things atomically. It goes to sleep and it releases the lock. If it went to sleep and didn't release the lock, bad things would happen because no one could ever get back in the monitor. And we'll actually talk about that as a problem later with some of the very simple Java concurrency models. Here's another little thought question. Under what circumstances might the first thread, thread 1, which had been waiting, wake up and not be able to get the resource it was trying to acquire, and therefore have to go back to sleep again? What would be the situation under which that might happen?
If something like notify all was used and another thread had grabbed the resource before.
Right. You may be awakened from your sleep, but by the time you go to grab that resource, someone else has come by, either because they woke up first or because they had a higher priority or whatnot, or just the vagaries of thread scheduling, and someone got there first. So you can't bank on there always being the resource, even though you were awakened to do that. And I'll talk more about that when we get a little bit further along. Okay, any questions about this? This is very, very important to understand these steps. Once you understand this, kind of like the classic 70s TV show Kung Fu, right? You know, when you can snatch the grasshopper, or you can snatch the pebble from the master's hand, you can go to the next level of enlightenment. In this particular case, understanding these steps is very important. All right, yeah, Sean.
Can you go back?
Yeah.
Why is it that the second thread notifies before it releases the lock?
Great question. Very, very long history of that, because if it releases the lock first and then notifies it, the piece of code may be unlocked for a period of time, and strange things can happen. So there's a lot of discussion in the monitor object literature about this particular optimization, and if you're not careful, it can lead to something called the lost wake-up bug. And so even though it seems somewhat less efficient to signal and then release the lock, it turns out in most implementations it's a very good idea to do it that way.
Is it possible, though, that if you notify before you release, that the thread 1 that is now reawoken will try to access it, find that it's still locked, and will lose its priority?
No, it won't. It could lose its priority for various reasons, but it may be awakened, but it has to then wait in a different queue to get access to the unlock of the thread. This kind of thing would typically only be an issue if you had lots and lots of CPUs where things really woke up instantaneously. Usually the amount of time between when you signal and when you release the lock is infinitesimally small. And so by the time you actually wake somebody up, the lock has already been released. But that's another reason why you always have to check that condition, because someone else may have snuck in faster to get the lock and grab the resource before you did. But that's a great question. There's a number of interesting uses of the monitor object in Android. Surprisingly enough, there's not a lot of uses of sort of the canonical case where you've got a synchronized method with wait and notify, especially in the framework part of the code. And there's a variety of reasons for that, most of which have to do with the fact that the framework part of Android often doesn't use a lot of threads. It's kind of expecting to be running in the user interface thread. And so you actually have to look other parts of the code to find more advanced uses of monitor objects. So one example that's kind of cool is the cancellation signal class, which came along. It looks to me like it came along in Android 4.1, the Jelly Bean release. When I looked for it in Ice Cream Sandwich, I didn't find it, I didn't look very hard. And basically, it's a class that's defined in Android that allows a caller to cancel a long-running operation. So let's say that you were trying to do some kind of query operation on a content resolver, which is something that accesses typically a database under the hood. And you start this query, and it's taking a long time to run, and you're like, you know, the heck with it, I just don't really feel like waiting around for this thing. So you can actually cancel this. And there's a method, if you take a careful look here, this is the method for query. This is a documentation for the content resolver query method. You can see the last parameter is the cancellation signal object. So you can make a cancellation signal, and then you can later cancel it. And when you do this, some interesting things happen. A cancellation listener will be called, and it can do something to basically cancel the query and get things so that it'll return without running for its full length of time. Now, there's a couple of things to note here. First of all, this is typically code that's done by infrastructure software. You as an application developer rarely use this, but the infrastructure may use this to clean resources up in various ways. And there are two important methods that we're going to focus on to illustrate the use of the monitor object pattern. The first one is called setOnCancelListener. And the onCancelListener is a callback which is going to be invoked when this cancellation takes place. And when this cancellation takes place, that typically will go ahead and release whatever resource or free up things so that you stop the query or whatever you're doing. Cursor loaders, I think, also use this mechanism as well. So let's take a look at the setOnCancellationListener. As you can see here, it doesn't actually use the synchronized keyword in the interface or in the method signature. It uses it in the implementation. And I haven't shown the entire implementation. I'm just focusing on the part that shows the monitor object pattern. So what it does is it comes in here, and it goes ahead and synchronizes. And then it says, while someone is trying to cancel this particular method or this particular operation, wait, because we don't want to change anything while we're in the middle of canceling. Remember, this method is going to set a cancellation listener, and if there's already a cancellation taking place, we don't want to rip the cancellation listener out from underneath what's already there and replace something else, because crazy things will happen. You'll end up with all kinds of race conditions. So while cancellation is taking place, wait, and then when cancellation is done, we can go ahead and update the cancellation listener, which we stashed away here as a variable somewhere, with this callback handler. So that's what set on cancel listener does. The cancel method is also a synchronized method in the monitor object pattern. And you can see what it does is as follows. It comes in, and it's actually got a couple of synchronized blocks in it. The first thing it does when you call cancel, it grabs the lock, which means that we're about to protect the internal state, so other threads can't mess with it while we're doing anything. It sets mCancel in progress to true. This means something is being canceled. When we set that thing to true, then this guy, of course, is going to loop as long as that's true. We then do some work, and one of the things we do is we call the onCancel hook, which was supplied earlier when we set the onCancellation listener hook. And that'll do whatever it needs to free up the resources, shut things down, clean up whatever we need to clean up. And then, no matter what happens, whether an exception is thrown or we just fall off the end of this particular try block, we come back, reacquire the lock, set cancel in progress to false, and then we notify anybody who is waiting for cancellation to be finished that they can proceed. So that notify all will end up waking up the thread over here, or any threads over here that may be waiting, in order to be able to let them go ahead and set a new cancellation listener. So it's just kind of a classic example of the monitor object pattern. We have only one thread at a time that can be active. You can see how we use synchronized blocks to get fine level control over synchronization, and we use wait and notify to make sure things happen in the right order at the right time without stomping on each other. If you're interested, the source code for this is all available in the Android release, at least the Jelly Bean stuff and later, and it's worth taking a look at how it works. It's pretty cool. And you can also search in the Android release and see where this code is used, because it's used in things like the content resolver and content provider and this SQL connection handler stuff and so on. Okay, so there's a number of consequences of applying this particular pattern. And let's talk about them, and then we're going to talk about some implementation strategies and implementation techniques. So one consequence is that it tends to simplify the design of your software. In particular, it gives you this nice programming model where you're making method calls on objects, and synchronization, by and large, is occurring at the method boundary. Now, as you saw, we could actually have multiple synchronization points using synchronized blocks within the methods, but the point is the method call is what the client sees when we invoke these operations. We can also have a fairly straightforward way of being able to allow methods to coordinate the order in which they run and the conditions under which they're allowed to run. So if we take a step back and look at the example from before with put and take, you'll see here that we have the synchronized method put, and it will do some things and will notify anybody if when it's done adding stuff to the message queue. Likewise, take will sit there and wait while the queue is empty, and when the queue is no longer empty, it can go ahead and remove an item from the queue. More sophisticated implementations do a better job of optimizing this stuff, and we'll take a look at that in a second when we take a look and see how the code looks internally to the Java concurrency library implementations. There's some downsides, however, with using this particular approach. One of the problems here is that if you're not careful, you can have lots and lots of threads, but those threads then end up having the monitor object itself become a contention point, because you could have dozens or hundreds or thousands of threads, and there's one poor measly monitor object, and they're all trying to descend, and it can easily become a point of contention, a bottleneck, and other kinds of problems. In that case, the monitor lock is a choke point in the scalability of the design. Does anybody have any thoughts about ways in which you could address the issue of choke points or contention points in a concurrent design? The most common thing that you do is you start to partition up your data space so that you have multiple monitor objects. So as a simple example, let's say you're looking stuff up in a dictionary of some kind. The most obvious thing and simple thing to do would be to have a dictionary with a single lock, and all the lookups have to go through that particular place. So if you have a bunch of threads and they're looking up words in a dictionary concurrently, then they'd all descend on one thing. So one observation you might have is, well, why do we need to really even use sophisticated locking mechanisms? We could use a reader's writer lock where you could actually have multiple readers going simultaneously, and only if we ever update the dictionary, which would probably occur very infrequently, would we ever have to actually block anybody out. So one thing to do is use a more scalable locking mechanism. Another thing to do is to take some advantage of the data itself in order to partition the search space up so you don't have all the threads descending on one lock. As a simple-minded example, you could have a monitor object for every letter in the dictionary. So you'd have the A, all the A's would have a monitor lock, all the B's would have a monitor lock, all the C's would have a monitor lock. And so you could take a look at whatever you were looking up, and then you would go and use the monitor lock on that particular, or the monitor object on that particular letter. And that way you would partition the data space to be more granular, so you could get more searching done more concurrently. There is no one right-size-fits-all solution here, and there's actually lots of good literature on concurrency patterns for dealing with scale. But the point is that you can end up with contention if you're not careful. Another issue, which is rather subtle, has to do with so-called extensibility semantics. There's something that's been in the literature in the object-oriented programming community for many years called the inheritance anomaly problem. And stripped down to its essence, you can read more about it here at this paper, which gives I think it's a PhD dissertation about trying to address inheritance anomaly. It basically says if you tightly couple your logic, your business logic, with your synchronization logic, then if you want to make changes to either one, you'll end up with problems if you try to use inheritance. And so there's a whole lot of work that's been done trying to solve the inheritance anomaly problem. Probably the best thing to do is not to use inheritance as your means for extensibility. Use some kind of strategy pattern or some other means to plug in either locking strategies or behavioral strategies or whatnot, and then you may be able to get a better way of doing this. Like the template method pattern or the strategy pattern may give you some help in some of these things. Another very subtle problem occurs a lot in Java. If you're not careful, if you use the simple built-in mechanisms, this is called nested monitor lockout. And it'll trick you and trap you in all kinds of subtle ways. So here's a particular example of this where we have an outer class, or we have an inner class that uses synchronized methods to do various kinds of things, and we have an outer class that creates an instance of the inner class. And the problem we have here is if somebody calls the process method in the outer class, and it turns around and forwards down to the inner method in the inner class, the outer method's monitor lock is held. And even though the inner class's method may do signals and notifies and so on, the outer lock is held. So if somebody tries to come along later and make some change to the outer method, that lock will still be held. There's a whole bunch of different ways to address this problem. I wrote a paper many, many years ago, about 15 years ago, that talked about this problem and described a couple of different ways of doing lock sharing in order to get around this problem in Java. The better way to do this often is just not to use the built-in mechanisms in Java at all, and instead use some of the things that are defined in the concurrency utilities part of Java, which we're about to talk about. So to make that latter point crystal clear, here's an example of how there's a piece of code from the Java util concurrent implementation, which implements something called an array blocking queue, which is very much like our synchronized queue that we looked at before. This is just what's built into the Java concurrency libraries. So you can see the array blocking queue is a generic type that extends abstract queue, implements blocking queue, and also provides some serializable capability as well. And what it does is it is a queue that's backed by a bounded blocking queue. That means a queue that has a fixed amount of space allocated to store information in it. And it queues the elements in first in, first out order. So it's a FIFO queue. And the property is if the queue is empty, like we talked about before, it blocks till the queue is not empty. And if the queue is full, it blocks until the queue is not full. So the first thing you do is define the interface methods, put and take, just like our example before, except they're generic. The next thing we do is we define our implementation methods, which in the case of the array blocking queue are called insert and extract. And we're going to look at these in more detail in a second. This particular way of doing things, having interface methods and implementation methods that are private, is something that's called the thread-safe interface pattern. That's another POSA2 pattern. In the interest of time, I'm not going to define it right here, but you can take a look at the link and learn more about thread-safe interface. It's a very useful idiom to simplify concurrent application code. The next thing that you do is you go ahead and you implement the internal state and any synchronization mechanisms or serialization mechanisms you may need to get the job done. In our particular case, we're going to use some classes that are defined in Java util concurrent lock, and we're going to pick the lock method as a reentrant lock, which means that you can have recursive calls. As you call up a call chain, a call stack, you can call the lock method multiple times without it deadlocking on itself. And we're also going to define a pair of so-called condition variables. Condition variables are things you can use to put yourself to sleep until things look more like what you'd like them to look like. So we have a lock variable, it's a reentrant lock, and we have two conditions, not empty and not full. And all this code is straight out of the Java Android source code. And then we go ahead and we implement the various methods that we need using the synchronization mechanisms we talked about. Notice here that we don't use the Java synchronize keyword at all. If you take a look around in the way that really expert programmers work, they don't tend to use synchronized a whole lot. Here's basically what they do. Here's the put method implementation. You can see it comes in here, and it goes ahead and it acquires the lock. So it doesn't use the synchronized block. It says lock interruptibly. And then it goes ahead and goes into a try block. And while the count is equal to the length of the number of items that we can store, it's going to wait for the queue to be not full. So when you try to put something in the queue and it's full, it blocks until it's not full using the await call, which is basically the monitor object wait that we looked at before on a monitor condition. When it finally gets through that particular loop, it inserts the element into the queue, and then it goes ahead and unlocks the lock. And then it's done. Here's the take code. What take does is it comes along. It also manually and explicitly acquires the lock. And then while the queue is empty, while count equals 0, while the number of elements in the queue is 0, it awaits not empty condition. So we have not full and not empty. And we have these two conditions. And this allows us to be able to use somewhat lighter weight mechanisms to be able to do this. Now, if we were to go and actually look at the code, you would see in the method for extract and insert that they're calling notify in order to wake up people who are waiting. When you insert something in the queue, you're going to go ahead and call the notify method on the not empty condition. When you take something out of the queue, you're going to notify on the not full condition. And those are the ways in which you alert the various callers to cooperatively schedule their interactions. So I encourage you to take a look at the Android code. If you Google this path name, you'll find it. It's instructive to take a look at it. But it's kind of cool because they don't use the basic built-in Java mechanisms. They build their own because that gave them the flexibility and performance that they needed to have. There's a number of known uses of this pattern. The classic Dijkstra and Hoare style monitors are good examples. Take a look at this link. You can find more about that. The metaphor that they typically use here is one of a room with doors. And when you enter the monitor, you can go ahead and be in here when you get permission to run. And when you wait, you step outside into a little waiting room. And when you're signaled, you can go back in, and you can signal other people, and then so on and so forth. So that's kind of the metaphor to think about. Only one thing in there at a time, and you can step in and step out. Java objects with synchronized methods. As we were seeing before, in practice, you don't tend to use the synchronized methods or even the synchronized blocks sometimes, but it's still valuable to know that this exists. We saw Android's cancellation signal as an example of using the monitor object pattern in Android. And then I developed whole piles of basic building blocks that can be used to implement monitor objects in C++. And there's lots of other examples of monitor objects in C++ that you're likely to find if you poke around long enough. OK, so to summarize this discussion, concurrent software often contains objects whose methods need to be invoked by multiple threads at a time. And we want to be able to protect the state of those objects by using some kind of synchronization mechanism. And we'd like to not have clients know this is taking place because it would require them to have too much knowledge of how the synchronization locking protocol works. We want to encapsulate that behind the scenes. And the monitor object pattern is used to basically share objects between multiple threads while still preserving a nice object-oriented programming abstraction. Okay, and that is the end of today's lecture, right about on time. Any questions about that?